Welcome everybody to this first webinar in chromatography of 2019. And this is on a great topic. It's practical UHPLC, selectivity, rapid method development, method translations, and also instrument transfers. So there's quite a lot of information there, quite a bit for us to get through in the next 45 minutes or so. So today's talk is going to cover all of those areas, and I'm going to begin with a very brief introduction into UHPLC and how it can help us. I'm going to move on to how we can use HPLC and exploit it for very high resolution separations, and I will include hints and tips throughout the talk. I'm then going to talk a little bit about method development and how we can use selectivity to help us. I'm also going to then move on to how we can translate methods from HPLC to UHPLC. What are the things we need to consider? What are the tools that we can use and that are available to help us get as accurate translations as possible, particularly to use the speed advantage of UHPLC. And finally, I'm going to talk about a topic which I know many people have challenges with, and that is moving a particular method, once you've developed it, between different types of instruments, different vendors or binary and quaternary systems and so on. And then I will finish up the talk and then hopefully the questions will have been answered through the talk. If there's anything left, then we can answer them at the end. So how can UHPLC help us? Well, UHPLC typically with smaller particles, the sub 2 micron particles are very popular, give high performance, much higher performance than HPLC typically. Of course, there are some caveats with that, such as the fact they generate higher back pressure. Now, the use of small particles has been around for a very long time, and it is grounded in very sound chromatography theory. The efficiency, the number of plates of our separation, is inversely proportional to the particle size. So as we decrease the particle size, the efficiency of our separations increases. So in fact, if we take a 5 micron particle and we reduce it to a 1.7 micron particle, then essentially our efficiency can increase by up to 3 times. Now, with that opportunity, we can also look to reduce our column length if we want to. And if we reduce the column length by a third, for instance, then we'll typically get a very similar efficiency. But of course, the runtime will be a lot less. So UHPLC provides us with the opportunity to do analyses faster with similar performance. So for instance, we can see there at the bottom of the slide, 150 millimeter column, 5 micron particle is approximately similar in performance as a 50 millimeter column using a 1.7 micron particle. But the big difference is the runtime. We will be able to do the analysis much faster. And this is based in good chromatography theory. So UHPLC offers us a number of different advantages over HPLC, and I've listed 4 of those advantages here, which I'm going to briefly touch on to begin this talk. There is the speed of analysis and the opportunity that we can do things much faster. There's higher resolution, potentially with smaller particles. We can do ultra high resolution separations with longer columns, which I'm going to give a nice example for everybody to see. And then also, of course, all of these things come together to give us overall an increased productivity of the analytical laboratory. That might be in time, but also in solvent saving, cost savings, and so on. The first thing I'm going to do, though, is ask everybody to complete a poll. And this poll, I will only have it on the screen for about a minute or so. But if you could answer this question, it would be very helpful because it gives us a good idea of if you currently do UHPLC in your lab. Is this a technique that you use routinely in your laboratory? And that would really help. It gives us a good idea to know what our audience is like, the techniques people are using in the laboratory. And so this is useful then for us to understand, okay, what are the type of topics that people want to hear about? What are the type of things that people want to for us to talk about? So we're still collecting some responses now. I'll leave it open for a few seconds more, for around another 10 seconds or so, and then I will close the poll and move on with some practical examples of those 4 key areas that I talked about. Okay, so please press your button and I'll stop the poll now. Okay then, so if we move on with the webinars, just got some technical stuff going on here. Okay, there we go. If we move on with the webinar, so first of all, I talked about speed of analysis. So if we look here, we can see a very simple gradient separation, HPLC base with 10 components. Now in gradient chromatography, it's more accurate to talk about peak capacity, PC. So you can see the peak capacity values for the average peak capacity across the separation, and also for one of the specific analytes calculated on the chromatograph. Now this is an HPLC base separation, and of course we can translate this to a UHPLC separation, and we can see here the use of a 50 by 3 millimeter column, 1.7 micron particle, and you can see that we get a very nice increase in the speed. So instead of this separation being around about 25 minutes, we still have full resolution, full separation of our components, but we're probably talking about 3 or 4 minutes. So UHPLC is offering us that speed advantage. And the resolution, the peak capacity values, you can see there are approximately the same. So we don't lose very much, but we gain a lot in terms of speed. Now, of course, we can use UHPLC for improved resolution as well. And on this right-hand side of the slide, you can see we're using a 100 millimeter column, and we can see that we're getting a higher peak capacity values. So you can see on the chromatogram there, the average peak capacity now is 320 compared to the HPLC separation where it's 213. So approximately 50% improvement in peak capacity using the longer column, but also with the 1.7 micron particle. And in fact, we can see that more clearly if we interrogate the data a bit more closely. We can see the peak resolution values for the peak pair 1 and 2, for instance, on the HPLC separation, the 154.6 are lower than those for the 100 millimeter UHPLC separation. And further on in the chromatogram, peak pair 8 and 9, we can see again the HPLC values are 8.2, and they're higher with the UHPLC column configuration. So certainly speed and resolution are advantages of UHPLC. What about very high resolution separations? Well, here we have on the slide here a natural product echinacea. And if we do a broad scouting gradient run, this is using a solid core type column, we can see we get a chromatogram with a whole host of different peaks, a sort of a different profile, and it gives us some useful information. And I've picked out a couple of peak pairs there. You can see the resolution value is 1.2 with a peak capacity of 513. Now we can use good chromatography theory, and we can translate this method onto a longer column. And essentially what we can do is couple together two columns. So we essentially have a longer VM term in the equation that's at the top of the screen. That's the column volume value. But we've got to keep the equation balanced. So if we change the VM term, then we need to change the gradient time term and keep the flow rate the same. And if we do that, you can see now, so this means that the selectivity of the separation is the same. The K star, the retention in gradient chromatography is the same. You can see now that we've improved the resolution of that peak pair. And you can also see the peak capacity values increased now to nearly 700. And we can do the same transformation again, but now with 3 columns. So we've essentially now got a column that's 450 millimeters long. And we can see that we've got a resolution of over 2 between the peak pair that I've picked out and a peak capacity value of over 900. And this is using those simple equations to make sure that the selectivity stays the same, but every time we increase the VM, the column volume term, we have to make sure we modify the TG term. And in fact, if we zoom in on the detail of that red box that I showed in the previous slide, you can see how we're getting more detail in the smaller peaks as we increase the column length. And you can see we're getting improved resolution of that particular peak pair. So this is a way that we can use a higher performance systems, higher pressure systems to give us detail for complex samples. Now, of course, productivity is important to everyone in their laboratories. So how can UHPLC help us here? Well, on the top chromatogram, we have a standard HPLC separation. You can see this is a simple gradient analysis of some peptides. And we can see the chromatogram underneath. If we translate that to UHPLC from a 154.65 micron HPLC to a UHPLC 50 by 3 millimeter 1.7 micron, we can see we benefit from that huge improvement in the reduction in the runtime. If we zoom in and you can see the gray box where we can see the actual separation, you can see that we've preserved the chromatography. The critical pair in the separation, the closest diluting compounds in the chromatogram, peaks 2 and 3. You can see that we still have a resolution value of 3. So we've maintained the quality of the separation. So that means we can do more injections per unit time, we can do more samples per unit time. And in fact, if you look at the statistics and the data, you can see there's an 85% reduction in the runtime and also the solvent use. So UHPLC can provide us with these opportunities. So that's a very brief overview of some UHPLC benefits. What about some practical hints and tips? Well, first of all, filtration. This is a very important one. So it's really important to filter your mobile phases and to filter your samples. You should replace your mobile phases regularly, in particular with UHPLC. It's a technique that requires very high levels of cleanliness and housekeeping to ensure you get good performance out of your columns and your instrumentation. And of course, there's a variety of different filters and filter systems available to make sure that your mobile phases and your samples are as clean as possible. And the bottom comment that I've made there about high quality solvents, this is really important to make sure that you can purchase the best quality solvents that you can for your separating systems, in particular for UHPLC and for LCMS. You want to reduce any likelihood of impurities affecting your chromatography or your MS signal. Of course, you want to make sure that you reduce any possible contamination in your mobile phase reservoirs by using suitable cap systems and coverings and so on. And on this slide here, we've got a few different examples here where we're just making sure we're using filters on our reservoir systems and also different types of cap systems to make sure that we're trying to remove the likelihood of dust and other material getting into our solvents, in particular the highest aqueous components, as it's not unusual for bacterial and microbial growth to cause problems, particularly if you use 100% aqueous in a particular line. And you can see there as well, it's always good practice to use solvent cap systems on waste containers as well to reduce the likelihood of volatiles in the laboratory. Use the highest grade water that you can, but even when you do, it's important to make sure the water is suitable quality, because you can see here, this is some examples from real life data generated in the lab, and you can see that obviously source A bottled water was not quite as clean as source B. So even though we are buying bottled water, we're not using other types of systems or tap water or anything like that. It's important to make sure that your bottled water is of the best quality that it can be. For organic solvents, again, it's not unusual to see issues in gradient chromatography if you're using lower quality or lower grade solvents. And you can see here an LC UV trace for different grades of solvents. And we can see quite a difference, particularly as the solvent goes to higher % Bs in the chromatography. And also, this is especially important for gradient analysis and LCMS work. And here we can see again some solvent background interference from different grades of organic solvents. So if you can, use the highest quality. This is particularly important for UHPLC and LCMS type work. So let's move on to a brief couple of slides on method development. So again, just before I move into the detail of this, what I'd like to do is just run another poll, just so we can understand which of the people who are listening today do method development. So if you could look on your screen now, and if you can answer the question on whether you perform method development or not, this is helpful because it helps us understand a bit about the type of work that you're doing, and also make sure that we're talking about the right topics to you, the things that are relevant and are going to make a difference to you. So whilst that poll's running, I will run it just a little bit longer, just to make sure that everyone has a chance to answer and register their vote. Most of the people listening to these talks are method developers, but of course there are people out there who don't have the opportunity to do method development but are still interested as well. So we want to make sure that we're capturing the right people with the right information and giving you the practically useful stuff to help you do your job. So I'm going to close that poll now and move on to some of the details. Okay, so that's the poll closed. So moving on to the method development topic. So this is one form of the resolution equation, and we can see here that it has three components to it: an efficiency component, a selectivity component, and a retention component. But we can see it's difficult to interpret which of those three elements of the equation contribute the most to resolution. If we look at the graph on the right-hand side of the slide, we can see quite clearly that selectivity really is important in chromatography. In fact, selectivity is the key to analyte resolution, as I've written on the slide. So whenever we're doing method development, we should be thinking about those parameters that maximize selectivity. If we focus on those parameters for our method development, it's going to help us develop our method much more quickly. So we know that selectivity is important because theory tells us that. So what parameters affect selectivity? If you look at many of the parameters that you can change and modify in chromatography and method development, you can see that most of those parameters have an effect on alpha, or selectivity. The key thing to remember is that not all parameters affect selectivity to the same amount. So you can see on the slide now, we've got isocratic separations on the left, and these parameters are in a list format. So the parameters at the top of that list, the column stationary phase, the organic modifier, and the pH, these have much more of an impact on selectivity than the parameters at the bottom. On the right-hand side of the slide, we have gradient separations, and you can see that we have some additional parameters that can affect selectivity there too. Now, for this particular talk, I'm going to focus on column stationary phase and how the chemistry of your column, or more accurately, the mechanisms of interaction, can help you maximize selectivity and develop your methods faster. There are many different types of stationary phases available. There are traditional phases and there are novel chemistries. Traditional phases include the C18 column, which is the most widely used column in the world in many different application areas. Now, with the ACE portfolio, we've tried to design different types of chemistries that bring together different mechanisms of interaction to maximize selectivity. And we use these in a screening type approach. This is a semi-automated way to do method development. These different chemistries give you different selectivity, which maximizes resolution of your compounds in your method development. Many of these phases have been demonstrated in method development to give you separations that are not achievable using a standard C18 column. These phases are available in a wide range of UHPLC and HPLC formats. So these are the structures of the novel chemistries, and you can see there's 5 different chemistries listed down there, and they all have been designed with a purpose in mind for method development. And I'm going to show you an example of how you can use these in combination with solvents and methanol and acetonitrile to give you a method development platform. Now, the way that we know that there's different mechanisms is that we can characterize the columns to help us understand different mechanisms of interaction with different column chemistries. This is a published approach to understanding mechanisms with LC column chemistries. We use what's called the Tanaka characterization approach, and I've cited it at the bottom of the slide there. And this was published a long time ago, and it's simple but a very powerful way to understand which are the dominant mechanisms with different stationary phase chemistries. And you can see I've listed 6 different column chemistries there, and you can see that more stars means that that mechanism is more important or more dominant with that particular type of column chemistry. So you can see that, for instance, with a standard C18 column, it is dominated by hydrophobic interactions. This is something that we all know. It is an alkyl chain with 18 carbons long. It is lipophilic and is dominated by hydrophobicity. Of course, a C18 column has no aromatic regions, so there's no pi system interactions. There's no polarizable functionality, so there are no dipole-dipole interactions. And you can see that there's a small amount of hydrogen bonding, which is provided by the silica surface. And then also many C18 columns have a small amount of shape selectivity, and many people don't realize that. So that is the C18 column, which is the thing that most people use. Now, obviously, it makes sense when we're doing method development to use different chemistries with different mechanisms to maximize selectivity. This helps us develop our method far more quickly, and we can combine the right column together with the different types of analytes. So together as a screen, different column chemistries or different mechanisms are very helpful, particularly when we use methanol and acetonitrile together in the same screen. We can set all of this up together on an instrument, and we can set up a sequence, load our samples, and press go and walk away, and the instrument will do the work for us. So this is an example of a screening system with the 6 different columns that I talked about, and this is for paracetamol and 9 of its impurities and degradation products. And you can see on the right hand side there, I've listed the columns: the C18, AR, PFP, the super C18, the C18 amide, and the cyano-ES. Each of these have different column chemistry and different mechanisms of interaction, and all of these columns are run with exactly the same conditions. So the only difference we should see is the interactions from the column chemistry together with the analytes. Now, as we look down each of the chromatograms, you can see we've got areas of coelution, which I've highlighted in red. And in fact, if we look at the number of peaks that are separated out of 10 across all 6, you can see actually there are 2 options, the C18 amide and the cyano-ES, where without any further method development work, we have methods available that separate all 10 components from each other. So this screening approach can be quite powerful, and this is in using methanol as a solvent. So 2 options just straight from the screen, no more method development required. If we look at this, the C18 column at the top of the slide here, this is the most common starting point for most people. This is where most people would begin their method development. And you can see that we have 2 areas of coelution, so further method development would be required. Whereas if the screen had been executed, we have options for our method straight from the screen, no further method development required. So that's for the methanol data. What about the acetonitrile data? Well, again, we have the same 6 columns in the same order, the same method conditions, but having the aprotic solvent acetonitrile instead of the protic solvent methanol. And if we look down the chromatograms, again, we can see different elution orders, different retention times, and areas of coelution. But in fact, if we look at the number of compounds that are separated with acetonitrile, there's actually 4 complete separations available using these general scouting conditions from this screening protocol with acetonitrile. So there's potentially 6 options identified from the methanol and the acetonitrile screen. And again, if we look at C18, we can see there's an area of coelution with acetonitrile, so further method development work would be required. Now, obviously, this doesn't work every time with every example, every application like this. For this particular sample with 10 components based on paracetamol, the screen worked really well. But there are other talks that I do where if we don't get a complete separation, what do we do next to optimize the separation? And that's the subject of a different webinar. But for today, what I wanted to do was describe that the screening approach is very powerful. It's very powerful because it's based on selectivity. different column chemistries and how the different interactions with your analytes and the chemistry can hopefully provide you with options for your method development and actual methods from the screen. So before I move on to the next topic, I want to run our third poll, which is just coming onto the screen now. And I'd be interested in your thoughts, if you can answer, please, on do you think that the screening approach would be helpful? Is this something that you think is useful and could be useful in your laboratory? I'll let that run for a few moments whilst we gather the different responses from the audience. Based on the screening that I've shown you and the data that I've shown you using that real data set, is this something that you think could be useful? Is this something that could help you in your method development, for instance? So I'll just let that run just for a little bit longer, not too much longer, as I realise we only have 45 minutes for the webinar this afternoon. But hopefully you can see that the chemistries and the mechanisms can be helpful in method development, but is it going to be helpful, do you think, for your situation? Is it something that you could find useful? Okay, so I'll just collect the last people clicking yes or no, and then I will close that poll. Okay, so thank you very much for your responses, and I'll come back to the talk. Okay, so that was a short section on method development, and now I'm going to move on to method translation. So this is where we have a method, maybe in HPLC, and we want to take advantage of those things that I've talked about in UHPLC: speed, resolution, productivity. How do we do that? And I'll start off with simple isocratic translations. And the general rule of thumb for translating methods is to keep a constant length to particle size ratio, L/dP, and this is based from sound chromatographic theory. If you keep a constant L/dP ratio, then you should get similar performance with your UHPLC method. So for instance, as an example, if we have a common monograph method, 300 by 3.9 millimeter, 10 micron, sorry, that should say particle size, then this is approximately equivalent to a 150 by 4.65 micron particle size. They both are calculated out to 30,000. And in fact, if we plot this on the y-axis, you can see here this grid that I've created, particle size, and on the x-axis you can see the column length. So this is simply L/dP. Then you can see here where a 150 by 4.65 micron is equivalent, for instance, to a 75 by 2.5 micron, and it's also equivalent to a 310 micron as well. So all of these should give similar performance chromatographically. So once you've selected your new column format, your smaller column, your smaller particle size, because you want to perform your isocratic separations faster, there are a couple of different equations that you need to use to scale your separation from HPLC down to UHPLC, and those are the equations that are on the screen. You can also estimate the back pressure to make sure your system is suitable and to make sure you're not going to overpressure your system. And so what does that look like with an example? So here we have an HPLC separation on the top chromatogram, nicely resolved components by isocratic analysis using a 150 millimeter length column with a 5 micron particle size. If we translate that down to a UHPLC format, you can see we have a separation in around about 4 minutes. And if we zoom in and look at the details, we can see that the resolution value, for instance, between the first two peaks in the UHPLC separation is very similar, almost the same as HPLC. And also importantly, the performance of the separation, the number of plates of peak 6, you can see is almost identical. So that is a very well translated separation, and obviously our sample throughput would be much higher with the UHPLC variant. And of course, we have opportunities for savings in runtime and also solvent consumption. Now, the equations that I described to you a couple of slides ago, we've actually created a free tool for people to download. and there is a whole host of information in this tool. It's based in Excel, and you can see the exact separation I've just described and shown to you, inputted into the different boxes, and then it is translated automatically for you on the right hand side, and once you put your new column length and ID and particle size that you want. So this spreadsheet has all of those equations built in behind it, and we've extensively beta tested this, and it is free to download if you're interested. So that was isocratic translations. What about gradient translations? So there are some similar equations for gradient translations, but there's also some differences as well. And you can see there's a list of the different equations down there. So if we take a simple gradient separation, so these are peptides, so peptide separation, and we can see a nice gradient analysis by HPLC mode in around about 25 minutes or so. We can translate that to a UHPLC separation, and you can see that we've preserved the quality of the separation. The critical pair, peaks 2 and 3, are still well separated, and we're quite happy with that separation. And you can see as well that the runtime and solvent consumption have reduced quite dramatically too. So again, that's a very well translated separation. Now, there's another part of gradient translations, which is correcting your separation for the dwell volume to column volume ratio. And sometimes this is necessary to get the best accuracy of your gradient translations to UHPLC mode. And it's basically calculated by the equation that's on the screen. This is particularly important when you're translating to small ID and small column volumes, particularly for UHPLC. And the calculation is on the screen and is built into the spreadsheet that I showed you previously. And when you calculate the value of X, you either get a negative value, which tells you the injection must be delayed after the gradient starts, or you get a positive value, and essentially you need to introduce an isocratic hold at the beginning of the gradient. What this value does is corrects the gradient table to give you the same selectivity as the original separation, and I'll show you that with a very nice couple of examples. So here we have a separation, a gradient separation in HPLC mode, and if we translate that or calculate what the delay injection value is, we can see the numbers calculate to minus 0.62. So this means we need to delay the injection until 0.62 minutes after the gradient. So you can see there, if we delay the injection, you can see that's the actual separation translated to the 50 millimeter UHPLC column, and you can see that the separation has been quantitatively transferred from HPLC to UHPLC. Now, what happens if we don't include that correction for the dwell volume to column volume ratio? If we don't include that VD over VM correction, you can see we don't get the same selectivity. This is a very common area where people can't get good translations of gradient separations between different column formats, and it's typically because they don't include a VD over VM ratio correction. This is built into the spreadsheet that I showed you, and not all translators include this, but the one that I showed you that's free to download does include this correction as well. So there you can see the gradient translation, and you can see at the bottom right hand corner there's the calculation. The equations are built into the spreadsheet to calculate if you need to change your gradient table to make sure you get exactly the same selectivity as your original separation. So what about transferring methods between different instruments? What does that look like? What are the challenges there? Now, if you're transferring an isocratic method between different instruments, then of course your method is going to stay the same. So your column format, the length, the ID, the particle size is not changing. So generally, no changes to the instrument are necessary. So this is switching between different instruments. It might be from your lab to an adjacent lab, your lab to a CRO lab, or your lab to a partner's lab, or whatever, in another country, another continent, it doesn't matter. If it's an isocratic method, then typically the transfer is quite simple because the method doesn't change. For gradient separations, it's not the same. And that's because you need to correct for the different dwell volumes of the system on the receiving instrument compared to your instrument, because of course the flow rate, the injection volume and the gradient times, your method all stays the same, but you have to account for differences in dwell. This way you can make sure you get the same separation on the receiving instrument as on your instrument in your lab. So if we start simply with an isocratic method, you can see here two different UHPLC instruments. And we can see that for this isocratic method, the performance of the method, the retention times of the analytes are almost identical between the two different instruments. So even though the extra column volume you see is slightly different between the two different instruments, there's no effects of dispersion on this particular separation. So typically isocratic transfers are straightforward. Now, gradient transfers are not because of dwell volume. So what is dwell volume? Now here we have a picture which explains dwell volume. So this is a binary pump, which is the most common pump type that people typically have in their labs. The dwell volume is defined as the point at which the solvents mix. So it's the mixer through to the beginning of the column. The volume between those 2 points is classed as the dwell volume. So this is for the binary pump. And here we have the quaternary pump, and you can see typically quaternary pumps have a higher dwell volume because they typically have a proportioning valve, because normally there's 4 different solvent reservoirs. They have mixers in place to ensure good mixing of the solvents, and so the volume is typically much higher. So when we're transferring our gradient method, of course, the method stays the same. So the gradient time, the flow rate, and the column volume are all identical. So we only need to correct for the differences in the system dwell, and we can see how we do that on the slide. And the X value that we calculate, we can see a negative value. If we get a negative value, the injection must be delayed. If we get a positive value, then we have to essentially introduce an isocratic hold. So let me give you an example of that first of all to explain what I mean. So for instance, a small column on a high dwell volume system, we can see here in this picture, we can see that actually we begin the run, the gradient actually starts, but the injection is made at some point into the gradient table. So we're actually injecting onto the gradients. This is when the value that we calculate is negative. That's what that actually means. For a positive value, we actually are injecting before the gradient begins. So we're actually essentially introducing or extending the isocratic hold on the gradient table. So this then, the point of both of these things is to make sure that we get the same chromatography, the same selectivity, because we have to account for the differences in the dwell volume between different instruments. So let me give you an example, because that's always the best way to explain a complex point. So here we have a gradient analysis that is very closely eluting peaks. And I've identified a peak pair with a resolution value of 1.7. And you can see the conditions, the gradient table are on the slide. Now our aim is to transfer from the quaternary system, where we develop the method, to a binary system of the same vendor type. So you can see we can use that equation and we can calculate out the differences in the dwell volume, and this comes to be a positive dwell volume, a positive value. So that means we need a pre-gradient hold. So if you remember from the picture that I showed you previously, we're essentially going to introduce a small isocratic section to get the same selectivity. So here we have the original separation at the top on the original instrument, and then the UHPLC instrument 2 in the second chromatograph. You can see if we do not adjust for the differences in the dwell volume, we get different chromatography. So obviously we would not be happy with that. You can see that the chromatography is quite different. We've got more coelution between the peak pairs that I've identified and changes in retention time as well. But if we introduce into the gradient table the correction factor on that same instrument, you can see we get exactly the same chromatography from the original separation on the quaternary system, UHPLC 1, to the binary UHPLC system 2, including the adjustment for the differences in the dwell volume. This is why it's really important to make sure that you consider this when you're moving a method between different instruments. Our selectivity is restored. And all of this is included in the ACE translation and transfer tool. There's a tab specifically for method transfer that talks you through what calculations or what data you need to make the calculations to make sure you get exactly the same chromatography. So finally, I'm going to show you on this particular slide, moving between multiple different instruments. So here is our original separation on a quaternary system. If we go to the same vendor instrument, but a binary system, so a lower dwell volume, you can see with an adjustment of 0.29 minutes, we have the same chromatography. It's quantitatively transferred. If we go to a different vendor, so this is a different UHPLC instrument now, it has a different dwell volume. We make the adjustment to the gradient table. We get, again, very good reproducibility of the chromatography from the original chromatogram, and we can go to a third UHPLC vendor. So we've got 3 different vendors of UHPLC instrument here. Again, a different dwell volume at 372 microliters, and again you can see the same chromatography. So with that small adjustment and using the tool that is free to download, you can see how you can make sure you get exactly the same selectivity between different instruments. It should really help when you're transferring methods between different places. So I'm going to run one last poll now, and then I'm going to summarize what we have talked about today. So thank you very much. The talk will be finishing in the next 5 minutes or so. So the last poll I'd like to run, you can see there is, do you perform method transfers between different instruments? There's lots of different people who listen to these webinars. Some people do this on a daily basis when they're developing methods and moving methods around instruments, around labs, between companies, and so on. Many people just do their own method development and their own sample analysis. But it'd be interesting for us to understand from the audience that are listening, is method transfer something you're interested in, you want to receive more information on? Is the technical information useful? Would you like further guidance, and so on? So thank you very much for registering your vote. I'm just going to collect the last couple of votes, and then I'm going to move on to the concluding part of the webinar. So thank you very much for everybody who has voted on that last poll. Okay, so moving to the conclusion and the summary. So hopefully what you've seen today is UHPLC can provide you many benefits. Increased speed, increased resolution, the ultra resolution angle if you couple columns together, and also productivity. It's without a doubt doing more per unit time as possible with UHPLC. Hopefully you've heard that stationary phase selectivity can really help you in method development. Those different mechanisms of interaction really can help you resolve the analytes in your samples, particularly when you're using phases that have been designed for that purpose, phases that bring together different mechanisms to help maximize selectivity. I talked a little bit about the translation of methods between HPLC and UHPLC using some simple equations. And for isocratic translations, it's relatively simple. For gradient, it's a little bit more complex, but again, it is straightforward, particularly if you use the tool that I've talked about. And of course, I talked about moving methods between different instruments and how this is also relatively straightforward if you account for differences in dwell volume, in particular for gradient methods. And I mentioned more than once, I'm sure, about the ACE LC translator tool. Please do have a look at that, download it, give us feedback. We always want to improve the usefulness of these things for everybody out there. And the last slide here is a little bit busy, but there's a whole series of different information, knowledge notes, some brochures and so on that you might find useful that I've touched on during this talk. Things like dwell volume, how to calculate dwell volume, extra column volume, the relationship with particle size and performance, different column chemistries, more information on column chemistries. All of this is available to download, or you can also email us at the email at the bottom of the slide as well. So with that, I'd like to say thank you. I hope this has been useful for you. I hope there's been something of interest that's going to help you as chromatographers in your lab somewhere, wherever you are in Europe. And with that, I'd like to pass back to the VWR guys, Avantor guys. Thank you very much for the opportunity to present. Back to you.